Hello geometry students, here's your lesson for section 4.9, Isosceles and Equilateral Triangles with Missy McCarthy, Math Instructor at Okemos High School. By the end of the lesson, you should be able to say, I can apply the Isosceles Triangle Theorem and its converse. I can apply the equilateral and equiangular triangle corollaries. Remember, corollaries is just another word for theorems. And I can prove the Isosceles Triangle Theorem. So an isosceles triangle we talked about before. The definition is a triangle with at least two sides congruent. Now, most of the time when we talk about isosceles triangles, we're talking about exactly two pairs of two sides being congruent, but it really is, the definition really is to at least two. So in this case, we have a leg congruent here and a leg congruent here, so the two congruent ones are called the legs. And then the one that is not congruent across the bottom is what I'm tracing here in purple. That is called the base of an isosceles triangle. So where the two legs meet, that's called the vertex angle, that angle right in there. And then where the base is, those are called the base angles. So those are the parts of an isosceles triangle. The vertex angle, the base angles, the leg, and the legs and the base. You can also turn the isosceles triangle on its side. When you turn it this way, you can see the legs are marked here in red. The vertex angle right here is at 3, and then 1 and 2 are now the base angles, making this the base of the triangle. So we have a theorem about isosceles triangles, and it says if two sides of a triangle are congruent, it means if it's an isosceles triangle, then it's okay to conclude that the angles opposite those sides are congruent. In other words, if you have an isosceles triangle, if a triangle is isosceles, then you can imply that the base angles are congruent. So if we have an isosceles triangle, triangle ABC here is isosceles, then we can conclude that angle B is congruent to angle C. So let's prove the isosceles triangle theorem. So what we have an isosceles triangle here, ABC, and we've drawn a line right down the middle through point X. Okay, so this line's going right down the middle, breaking our isosceles triangle into two triangles. So the very first thing we're told, one, is that AB is congruent to AC. That's given. Then 2, we know that, we know AX is congruent to itself by the reflexive property of congruence. Now, if we assume that we drew this line such that X is the midpoint, so let's say that that's what we did. We drew it so that X was the midpoint. That would be another one of our givens. X is the midpoint of triangle ABC. So X is the midpoint of triangle ABC. That would be given to us. Then if that's given, we can say that means that BX is congruent to XC. And that would be by definition of midpoint. So now we have 1, 2, 3 pairs of congruent sides. So we can say that means that triangle ABX is congruent to triangle ACX by side-side-side congruence. And if that's the case, then that means that angle B is congruent to angle C by CPCTC. So we've just proven the isosceles triangle theorem. All right, the converse of the isosceles triangle theorem is also true, which means if the base angles are congruent, then it's okay to assume that the legs are congruent. If two angles in a triangle are congruent, then the sides opposite those angles are congruent. In other words, the legs are congruent. So in this triangle, we definitely have an isosceles triangle. DE is congruent to EF, and we have to find the measure of angle F if we know the vertex angle is 22. So if it's an isosceles triangle by the isosceles triangle theorem, we know that angle D is congruent to angle F. So let's call both of those angles X. Now what we could do is use the triangle sum theorem and say X plus X has to be plus 22 has to be equal to 180. So that gives us 2x plus 22 equals 180. Subtract 22 on both sides and we get x equals 158. Divide both sides by 2 and we get x equals, see, 2 goes in there, 7 times 79. So angle F is 79 degrees. That's the measure of angle F. Here our isosceles triangle is on its side, so here are my legs, and I know that angle J, it has to be congruent to angle G. So I know angle J is 3x, angle G is x plus 44, and I know they are congruent. Angle G is congruent to angle J. So I could just say x plus 44 equals 3x. Oops, didn't mean to go to the next slide. X plus 44 equals 3x. Subtract x from both sides, I get 44 equals 2x, and x is equal to 22. So if x is equal to 22 and I have to find the measure of angle G, I'm going to plug 22 right back in there, which means the measure of angle G is 66 degrees. So that was using the isosceles triangle theorem. All right, we have two corollaries or consequences of the isosceles triangle theorem, which talks about equilateral triangles. And they're really, really simple. It says all equilateral triangles are equiangular and all equiangular triangles are equilateral. So if the sides are congruent, it's okay to assume that the angles are congruent and vice versa. So now we have an equilateral triangle and we need to find the value of x. Well, if it's equilateral, we know all three of those angles are congruent. And so we have three angles, and we also have a corollary way back when we learned the triangle sum theorem that said all of the angles in an equilateral or equiangular triangle are equal to 60 degrees. So I can say 2x plus 32 has to be equal to 60. Subtract 32 from both sides, and we get 2x equals 28. Divide both sides by 2, and x turns out to be 14. So we're using two corollaries there. Now this is an equiangular triangle, so we know it's also equilateral. So to find the value of y, we can just set 5y minus 6 equal to 4y plus 12. And that gives us y is equal to 18 if we subtract 4y from both sides and add 6 to both sides. So we have found the value of y using those corollaries. Alrighty, so make sure you can apply the isosceles triangle theorem and its converse. Use those corollaries for equilateral and equiangular triangles. And we just did the proof of the isosceles triangle theorem. See you in class.